pH, acid and base theory. The pH scale for aqueous systems runs from 0 to 14, with 7 in the middle being neutral, and as you head towards 0, those are acidic conditions, and as you head towards 14, those are basic conditions. And just be forewarned that the scale does go below 0 and above 14, but for our practical purposes, we're just going to stay between 0 and 14. An acid, according to Arrhenius, is any substance that produces hydronium ion in aqueous base solutions. Strong acids should be committed to memory, and they include hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, nitric acid, chloric acid, and perchloric acid. As seen by their formulas, what they all have in common is an H in front, and the H in front has the oxidation state of +1, and we now call that a proton. Your strong bases include hydroxides, sodium hydroxide, potassium hydroxide, lithium hydroxide, barium hydroxide, calcium hydroxide, strontium hydroxide, rubidium hydroxide, and cesium hydroxide. The most common one that we're going to use a lot is sodium hydroxide. And notice that some bases are what are called dibasic, and what makes them basic is the presence of the polyatomic ion hydroxide. So you should commit to memory both the pH scale, the strong acids, and the strong bases. Diving a little deeper into how acids form hydronium. This is the Arrhenius definition. Formulated by Svante Arrhenius in a long time ago. His definition only applies to aqueous or water-based solutions, and what Arrhenius says is acids in water will form hydronium, and bases in water will form hydroxide. And one confusing thing is, what is hydronium? So if we're talking about Arrhenius and we know we're going to invoke water, one thing you should get good at is math with letters. If you take a proton and add it to water, you will generate what's called hydronium ion. So using our prototypical acid HCl, if we see it with water, we are automatically going to invoke Arrhenius, and the simplest way I can state Arrhenius is an acid and water forms hydronium, and then by deduction you can determine that there must also be some chloride formed. And this is important as it's the amount of hydronium which controls the pH. So mathematically, pH is defined as the negative log of the molarity, as indicated by those brackets, of the hydronium ion. And we're going to plug some numbers into that, and you should get a feel for the numbers and what they mean. Importantly, as the amount of hydronium goes up, the pH is going to fall, and we say we're becoming more acidic. Mechanistically, it's often confusing how an acid gives up a proton to water. So if we draw a Lewis structure for hydrogen chloride or hydrochloric acid, and our Lewis structure for water, and we should recall that that's a covalent bond and that's a lone pair of electrons. And for HCl to release a proton, and the proton being a positive species, the covalent electrons between the H and the Cl have to go towards the Cl. And simultaneously, to form hydronium from water, a lone pair on the O of water must grab the proton from the HCl. And then we will end up with hydronium, and there is the new bond that we formed when the O of water grabbed the H of HCl as a proton, and then the Cl had 6 electrons as lone pairs, and by picking up that one, it now has its complete octet, and we call that a chloride ion. And this is very important, as all acids do this basic reaction. They don't all do it to the same extent. So this is a reversible or an equilibrating system, and different acids have different levels of conversion. For your strong acids, we can say they're fully converted, or we can say we can ignore the reverse arrow. Another way to say that is, if it's a strong acid, then the total amount of acid will be converted to hydronium. We're going to explore that momentarily after we cover how bases form hydroxide. What's very different about bases than acids is your bases are all ionic compounds. So a base like sodium hydroxide, being ionic, if we place it in water, and notice I'm invoking the H2O above the arrow, so now it's just acting as more of a solvent, not taking part in per se the reaction, whereas up here the H2O actually did partake in the reaction. And when an ionic compound dissolves in water, it also dissociates. And to dissociate means to separate or break apart the ionic bond. And that's a very important thing, a property of water, that it can dissociate a relatively strong bond, ionic bond between the sodium and the hydroxide. And recall that it does so by solvation. So because of water's polarity, having a highly electronegative O and an electropositive area between the two H's, it's able to stabilize both the hydroxide ion as its negative with water's partial positive charge, and it's also able to stabilize the sodium ion. If it weren't able to do that, then there would be no reason for the sodium hydroxide ionic compound to dissociate. Because as we know, energy controls all chemistry, so somehow what we have over here must be less energetic than what we started with, or else there would be no reason to go. And that is called solvation. So it's the solvation by water that allows these strong bases to, when they dissolve, to dissociate and thus release what we're going to call free hydroxide. Whereas with acids, they actually donate a proton to water, and the water is actually taking part in the chemical reaction forming hydronium.